Today's experiment is extraction. This is a new technique you are going to learn in this course. Extraction is one of the most important techniques for isolating and purifying organic substances. And in this method, a solution is mixed with another solvent, and those two things are immiscible with each other. So taking the advantage of that, the solute is extracted from one solvent into the other because it is more soluble in the second solvent. So that's basically the whole idea about this experiment. This experiment is divided into 4 parts: A, B, C, and D. Materials and chemicals used in this experiment: benzoic acid, caffeine, anhydrous sodium sulfate, methylene chloride, methanol, saturated NaCl solution, it is also called as brine, 1 molar NaOH, 1 molar HCl, 6 molar NaOH, 6 molar HCl, Di water, ether, unknowns, and separatory funnel. So you will learn the use of this separatory funnel in this experiment to do the extraction: ring stand and iron ring, melting point apparatus, thermometer. In addition to that, you would need like hot plate, test tubes, test tube rack, the stuff from your lab to do the experiment, from your drawer basically to do the experiment. Chemical waste. At the end of every part of this experiment, I will mention where you are going to dispose of your chemical waste. But in general, all the methylene chloride waste will go to the halogenated waste container. All the organic solid waste will go to the solid waste container, and all the aqueous waste will go to the aqueous waste container. Part A is basically the extraction of caffeine. In this section, caffeine is mixed with, first of all, with water, and then I'm going to add methylene chloride into that solution, and then I will try to extract so that caffeine will come into the methylene chloride. So that's how this is also called as liquid extraction, because two liquids they are used to extract a solute from one to other based upon the solubility. And I'm sure everyone heard about the decaffeinated coffee. So it is it is made basically using the extraction technique, very similar to what we are going to do in part A, extraction of caffeine. So in your pre-lab calculations, you need to find out the total amount of caffeine that can be extracted into the methylene chloride. So at the end of the part A, basically how much caffeine you should get, right? So that's this pre-lab calculation will give you theoretical amount of the caffeine. For that, you would need a constant which is called as distribution coefficient, and the value for caffeine between methylene chloride and water is 4.6. So in order to solve this question, basically the theory and the example is already explained on page 700. As you can see, 12.2. So it's very clearly explained what is distribution coefficient, how you can calculate, there is an example given and everything. So go over it, and if you have any questions, I'll be available for you to explain. So we are going to start the part A, and for that we would need caffeine. So you can see on the balance pan there is a centrifuge tube, and so that's the mass of the caffeine in the centrifuge tube. So now I'm going to add the 10 milliliters of water into this centrifuge tube, and then I will basically shake the centrifuge tube in order to dissolve it, and it will take several minutes to get dissolved. And if it is not dissolving, so you can always put the centrifuge tube into the warm water. So here I have already kept the water for on the hot plate. So that's how I'm trying to dissolve the caffeine. As you can see, it is not completely dissolved yet, and you can do the vigorous shaking, like this is the rocking motion. Now you can see the caffeine is completely dissolved. It took me about 3 to 4 minutes to completely dissolve the caffeine into 10 milliliters of water, and I slightly warm it, like for 30 seconds, 30 to 40 seconds. I slightly warm the solution in order to completely dissolve the caffeine. So this is the separatory funnel. We're going to use it in order to do the liquid extraction, and we would extract caffeine from water into the methylene chloride. So this is the ring stand, right? That's the iron ring. So that's basically the stand for separatory funnel. And this is the stopper, right? And this is the stopcock of the separatory funnel. When you start the experiment, when you want to add anything into it, make sure this stopcock is closed. Let's say if it is open, right? And if you want to add something, so accidentally you are wasting your solution, and make sure you should have something below the separatory funnel so that you won't waste your solution, right? And another thing is, it's closed, let's say, but you don't know whether it is leaking or not. So it always good practice to test whether the separatory funnel is leaking, right, or not. So I made this solution of caffeine in water. So it is best to use DI water to test the leakage. So I'll add a couple of drops. Right, so it's fine, it's not leaking. Now open it. Sometimes it is very tight, to open it. So I can open it and you can collect the solution. Right, so your separatory funnel is working fine. I'm going to now transfer the solution of caffeine into the separatory funnel. You can see my stopcock is closed, right? And we already checked that separatory funnel wasn't leaking. So that's how I'm going to transfer all of its solution. So now you can see I have already added my caffeine solution into the separatory funnel, and then I have a methylene chloride in 10 milliliter measuring cylinder. So I have 5 milliliter methylene chloride in it, and I'm gonna add that to separatory funnel slowly. Now you can see methylene chloride and water, right? They are not miscible with each other. So you can see clearly two layers. Since methylene chloride is a chlorosolvent, chlorosolvents are always heavier than water. Their density is more than water. So a lower layer is a methylene chloride, and the upper layer is basically aqueous solution, which is water. Caffeine in water. So now we are going to extract the caffeine into methylene chloride using the separatory funnel, by liquid extraction. So I'm going to do the rocking motion of the separatory funnel. And initially it is do it slowly, so that you would do one rock per 2 seconds, and then you would release the pressures. So you can, this is whoosh sound, right? So you need to do it until the whoosh sound is not audible anymore, right? So this is kind of mixing, and we should not vigorously shake it, because otherwise you might ending up forming the emulsion, and emulsion is kind of a third layer between the two. So do it slowly. Chlorosolvents, if you would vigorously shake them with water, they tend to form emulsion. So I'm gonna do it until I won't, hear any, whoosh sound. So now we are going to extract the caffeine into methylene chloride using the separatory funnel, by liquid extraction. So I'm going to do the rocking motion of the separatory funnel. And initially it is do it slowly, so that you would do one rock per 2 seconds, and then you would release the pressures. So you can, this is whoosh sound, right? So you need to do it until the whoosh sound is not audible anymore, right? So this is kind of mixing, and we should not vigorously shake it, because otherwise you might ending up forming the emulsion, and emulsion is kind of a third layer between the two. So do it slowly. Chlorosolvents, if you would vigorously shake them with water, they tend to form emulsion. So I'm gonna do it until I won't, hear any, whoosh sound. I was shaking it really slowly, right? One rocking motion basically per 2 seconds, and I can see that there is no emulsion is formed. So I can increase a little bit my rocking motion, like 1 rock per second, right? And then so in order to basically have an effective separation. A little bit, faster. You can see the 2 layers are completely separated, right, after the extraction, after all that shaking and the venting and all those things. So this is basically the methylene chloride, right, the lower one, and the upper one is the aqueous layer. So I'm going to use 50 milliliter aluminum flask, and then in this basically I'll slowly remove the lower layer and collect my first methylene chloride extraction. And towards the end, just close it and open it, close it, open it, so that you will not get the water layer sucked in. So this is my first methylene chloride extraction, right? And one important thing with methylene chloride, it is a toxic solvent. So make sure you do not inhale it deeply, right? And also another thing, when you would deal with the separatory funnel, make sure when you remove the lower layer from the separatory funnel, this stopper should not be on. Otherwise it will create the vacuum, and you will not be able to remove the lower layer effectively. So same way, I'm going to do 2 more methylene chloride extractions, 5 milliliter each, and then I'm going to pool all those 3 extractions here. So I have pooled all the 3 methylene chloride extractions into this aluminum flask, and then I'm going to proceed further with these extractions, because now my caffeine is here. So we did liquid extraction with water and methylene chloride. I extracted my caffeine here. Now this is my caffeine is into now organic solvent. I have forgot to mention before that every time when I did the extraction, I shook the separatory funnel for about a minute in order to get the effective extraction into the methylene chloride layer. Now this is my all the 3 extractions of methylene chloride. Right, so I pooled into the same aluminum flask. Now if you see clearly, there is still water droplets. You can see right there, right? So that's a water droplet. So what I will do, I will give again one transfer from this aluminum flask to this one, right? And then so that I wanna leave this water droplets behind in this flask, because my objective is to dry this methylene chloride. By using the drying agent sodium sulfate. So if I will add sodium sulfate to this flask, it will take too much of that compound. So the good thing is, first of all, I'm gonna make a transfer, leaving behind these water droplets, and then I will add basically the sodium sulfate in order to completely dry it. So that's how I'm transferring slowly to the other aluminum flask, to avoid any spillage. So you are going to keep both the flasks really near to each other, and that's how I'm going to transfer, leaving behind any water droplets. So I carefully transferred all the methylene chloride into the another dried Erlenmeyer flask, and you can clearly see that's the water droplet it left behind into the in the previous flask. The next step is to completely dry the all the three extractions of the methylene chloride by adding anhydrous sodium sulfate. There are various drying agents, but most commonly used drying agent is basically the sodium sulfate. So this happens when you would add the drying agent. As I mentioned before, you can use other drying agents as well. For example, magnesium sulfate can be added, calcium chloride can be added, but most commonly used is the sodium sulfate. So basically this is the anhydrous form. Solution contains a water molecule. They get associated with the drying agent, right? And you would get the drying agent now in the hydrated form, and the solution will be in the dry form. And that's our purpose of adding the drying agent. Now, how much drying agent needs to be added? Lab manual says that you should add 3 grams of the drying agent, but then the purpose of drying agent is to just dry this solution, right? And so that none of the water molecules will be there. So basically when you will add drying agent, and if water is present, it will form lumps at the bottom. So you can see that some of the drying agent is not very much free flowing, right? So they are kind of forming the lumps. So I'm going to add more. It's kind of now free flowing, I can see, right? Still it's a little bit lumpy form. I would add a little bit more. So what I will do at this point, I will close my methylene chloride flask, and then I will let it sit basically for 10 to 15 minutes. And if sodium sulfate will be clumped together at the very bottom and it's not free flowing at all, then I'm going to add more and let it sit. And in between you need to a little bit swirl it. So the solution of methylene chloride, it's sitting here for about I would say 5 minutes. In between I'm just slightly swirling it, and if you would see, the bottom is still the sodium sulfate is kind of free flowing. It's not clumped together, it's not forming lumps or anything more, right? So you can see some of the particles are free flowing. I hope you are able to see it, right? So but still I will give this solution more time, right, until 15 minutes are over, to so that all the water should go to the sodium sulfate and the solution will be completely dried. Since my solution is drying there, so I'm just taking the advantage of that time, and I want to show you that if you have water, like lots of water in the methylene chloride layer or any organic solvent, then how does sodium sulfate basically looks like when you will add it to that solution. So do you see that? It's all basically clumped together at the very bottom, right? It's not free flowing if you see. So it needs more water, sodium sulfate to remove all the water molecules out of it. So that is a reason I already transferred initially all the 3 extractions of the methylene chloride to the dried Erlenmeyer flask, so that I would not use so much of the sodium sulfate. Right, so now it looks like dried. You don't see that water droplet anymore, but it's still this it's not completely free flowing, so it does need more. You can see now it's free flowing, right? So now you can say it does not need more, and you can cover it. I'm doing in a beaker just to show, but then you can cover it and let it sit. And basically, if needed, you need to add more after waiting. Now, it's already 15 minutes, and then you can see the sodium sulfate is free flowing. It's not form any lump at the bottom of the conical flask, right? So now what I will do, I will transfer this dried methylene chloride extractions into the pre-weighed, dried and pre-weighed Erlenmeyer flask. This is the mass of the conical flask. Here I am transferring the dried methylene chloride extractions into the pre-weighed Erlenmeyer flask. Make sure these two flasks should be really close to each other to avoid any spillage or wastage of the solution. And make sure sodium sulfate should not sucked into it and come into the weight flask. Otherwise it will unnecessarily add to the weight of the caffeine. So I carefully transferred all the methylene chloride into the pre-weighed Erlenmeyer flask, as you can see right there. So now I'm going to proceed with this flask. So now it's time to basically evaporate the methylene chloride, right, which is in the Erlenmeyer flask, and make sure the temperature is about 45 degrees centigrade, and you are going to put your Erlenmeyer flask into the beaker, and once you see that caffeine, all of the methylene chloride is evaporated and caffeine left behind in the flask, so do not heat it more because caffeine will start supplying. So you do this step in full, right? Because methylene chloride is toxic, actually it is carcinogenic, so it's not good to inhale the solvent. Solvent is still evaporating and the temperature is maintained at 45, or I would say around 45 degrees centigrade. So as you can see, it is now completely dry. Methylene chloride is evaporating, and I immediately took off the flask from the water bath so that caffeine should not be supplied. Now I will let it sit here for 2 or 3 minutes because methylene chloride is a chlorosolvent and which is heavy. So I will give some time for methylene chloride to completely evaporate from the flask, and then I will dry the outside of the flask nicely, and then I will weigh it in order to calculate the amount of caffeine. This is the mass of the caffeine after the evaporation of the methylene chloride and the Erlenmeyer flask. So in order to get the amount of the caffeine, you need to subtract the mass of the empty Erlenmeyer flask. This is basically the caffeine, the extracted caffeine. You can put it in the recovered caffeine bottle. We are done with part A now, and this was the aqueous layer. So we can dispose of this aqueous layer now into the aqueous waste container.